Hello everyone. Let me start with a simple thought. Have you ever wondered why some stones sink instantly in water, while others, like pumice, actually float? The key lies in something called relative density. Relative density is simply the comparison of how dense a material is with respect to water. Instead of working with complex measurements of mass and volume, Archimedes gave us a practical method. By weighing an object in air and then in water, we can find this ratio easily. Mathematically, relative density equals weight of the body in air divided by the loss of weight in water. It's a ratio, so it has no unit, and that makes it a very convenient quantity. To see how this works, let's assign some symbols. Let the weight of a body in air be W1. Then immerse the same body in water, and its weight reduces to W2. The difference, W1 minus W2, is the apparent loss of weight, which equals the upthrust or buoyant force. So, relative density is simply the fraction W1 divided by W1 minus W2. Just two simple weighings, and the value is in our hands. This method is particularly useful for solids denser than water and insoluble in it. Now let's consider the first case, a solid denser than water and insoluble. We tie the solid with a thread, record its weight in air as W1. Then we immerse it fully in water, taking care that it doesn't touch the beaker walls, and we record its reduced weight W2. The difference, W1-W2, is the weight of displaced water. Dividing the weight in air by this loss gives us the relative density. As you can see in the diagram, the setup is straightforward, just a balance, a beaker of water, and the suspended body. But what if the solid dissolves in water? For example, salts or sugar crystals. In this case, we cannot immerse it directly in water. Instead, we use a reference liquid of known relative density in which the solid does not dissolve. Weighing is done exactly as before, but this time the formula slightly changes. Relative density of the solid becomes weight in air divided by loss of weight in the liquid multiplied by relative density of that liquid. This clever adjustment allows us to measure RD for soluble materials too. Let's work out a quick example. Suppose a solid weighs 50 gram force in air. When immersed in water, it weighs 40 gram force. The loss of weight is 50 minus 40, equal to 10 gram force. So relative density equals 50 divided by 10, which is 5. That means this solid is 5 times denser than water. This simple calculation shows how easily we can quantify density ratios using Archimedes' principle. While this method is simple, we must take precautions. The body must be completely immersed without trapping any air bubbles. It should not touch the sides or bottom of the container. Pure water at 4 degrees Celsius is ideal, since its density is exactly 1 gram per cubic centimeter. And of course, for soluble or reactive solids, we must pick a suitable alternative liquid. Otherwise, the experiment gives false results. So let's wrap this up. Relative density is defined as the ratio of density of a substance to the density of water at 4 degrees Celsius. Using Archimedes' principle, we can determine it experimentally with just two weighings, first in air, then in water. For insoluble solids, the formula is W1 upon W1 minus W2. For soluble solids, we adjust by multiplying with the relative density of another liquid. This method is elegant because it avoids the direct measurement of volume, which can often be tricky. I hope this session helped you appreciate how Archimedes' timeless principle makes relative density so easy to measure. See you in the next class with another fascinating application of buoyancy and fluids.